Hi friends, in this video I am going to discuss about maxima and minima of a function. So here maxima and minima, that concept arises from, for example, if you have some function y equal to f of x. So let's say here I will draw one function. So let's say this is my function. So let's say this is the graph of my function. So just observe one thing, and this is my domain. Here domain is my x-axis and here codomain is my y-axis. Here this is my origin. Let's say here I am taking the general value a. So let's say this is my function y equal to, here this is my function y equal to f of x. Here the function y equal to f of x from close interval 0 to a, let's say 0 to a, so which takes value from here. So here this is the maximum value, here this is one maximum value, so this is another maximum value, and this is one maximum value, and this is one maximum value. Let's say, so here this is one maximum value, so here this is one maximum value, and this is one maximum value, and here one more, this is one maximum value. So now from close interval 0 to here I will define sub interval C1. So from C1 to C2, let's say from C3, and let's say from C3 to CA. Just observe one thing, from close interval, let's say from 0 to C1, my function, so here so my function attains maximum value at this point, and minimum value, so here, and from C1, let's say from C1 to C2, so here, so I will define one more, here you can take one more, let's say C2, and let's say this is C3, and let's say this is C4, and let's say from 0 to C2, my function takes maximum value this and minimum value this. So here this is one minimum value, let's say from 0 to C2, my function takes one maximum value at this point and one minimum value at this point. This from 0 to C2, this is the minimum of all, and this is from 0 to C2, this is the maximum of all. In the same way, let's say from 0 to C3, so from 0 to C3, my function takes maximum value at this point one times, and this is one maximum value at this point. But here just observe one thing, from C1 to C3, so here I want to talk about this interval from C1 to C3. So this is my maximum value among all, so from C1 to C3. And now just observe one thing, so this is interval based maximum value and minimum value. Now so here from C1 to, let's say, C4, this is one minimum value, so here this is another minimum value, and let's say from here to here C3 to let's say here I will draw C5, so let's say this is my one another minimum value, and here so this is my one maximum value from, let's say, C4 to A. Just observe one thing, my idea is, so from close interval 0 to A, so here on sub interval, so let's say, so this is one maximum value above the x-axis, this is one maximum value from this interval, this is one maximum value from this interval, and this is one maximum value from this interval. But just talk about the whole interval, that is whole domain 0 to A. So here this is one maximum, this is another maximum, this is another maximum, but this, as compared to this two maximum, this maximum is greater than this maximum. So here let's say this is my A max here, and this is my B max, let's say this is my C max, and let's say this is my D max. Now as compared to this A and B, so this is more than B max. As compared to this C, so this is B max is greater than, so here this is greater than this is greater than this. But as compared to this 3, so here this D is greater than among all A max, B max, C max. So my A max, is the maximum among the all. So here A max is greater than A max is greater than B max, and B max is greater than, so here let's say C max, so here C max. In this way, my A max from close interval 0 to A, that is over entire interval, entire domain. So this point is my maximum among the maximum, that is my global maxima. So here I will call this D max as global, here global maxima, and so here this is we can say local maxima. So this is one point local maxima, this is another point local maxima, and this is another one point local maxima. But maximum among the maximum, that is global maxima. So this is my point. Now just observe one thing. So here from close interval 0 to a, so here this is one minimum. Let's say here this is one minimum. Let's say this is one minimum. So this is two minimum. Let's say this is three minimum. Now just observe one thing. So here this minimum, here this value of your function at some point. So this is minimum among the minimum. So here this is local minimum. So this is also local minimum, and this is global minimum. That is minimum among the minimum. That is here global minimum, and maximum among the maximum. That is global maximum. So here this is about maxima and minima on graphical. So here now I want to discuss. So here let's say when your function so let's say y equal to f of x. So this is here, let's say y equal to f of x. This is my curve. Here I am denoting my curve, and the rate of change, let's say dy by dx equal to, so here I will define as f dash of x. This represent the slope of the curve at particular point. So here, so this is one slope. So here this is one slope, this is one slope, from this is one slope, and this is one slope, this is one slope. So here f dash of x equal to, so here tangent to the curve. So here this represent tangent to the curve. You can say slope of curve. So let's say y equal to f of x. Slope of the curve y equal to f of x. Now here this is my slope of the curve. Now here if f dash is greater than 0, means my slope is greater than 0, and one another case is slope is less than 0, and third case is my slope equal to 0. These are the three cases arises. So here slope, this is my slope, that is there exists a tangent to the curve. So for example here I will draw the same curve over here. So here I will take one part over here. Let's say this is my so tangent. So let's say this is my tangent to the curve. Let's say here I am taking close interval a to b. Here let's say here I am taking t. So this is my f dash of c equal to 0. So that is f dash of c equal to 0, or you can say f dash of x equal to 0. So at this point, this is my slope. That is this slope is my this f dash of c equal to 0. This is the slope of the tangent at this point, and this slope, that is this tangent, is parallel to x axis. Means slope is 0. Now, so this is my another slope. Let's say this is my another slope, and let's say here I am taking one more tangent at this point. Now here just observe one thing. Slope angle measured by the positive direction of x axis. This angle is positive. Now here this is the slope. So here this is negative. So here you can measure this angle is negative. So here this is f dash of x is greater than 0. So when f dash of x is greater than 0, that is slope is positive at this point. At this point slope is positive. So here positive angle made by the line with x axis. So here this is positive. Now at that here slope is positive, positive, positive. So here this function is increasing. So here when your slope is positive, at that time you can say here function is increasing. Here function is increasing, and when your slope is negative. So here negative, at that time here this is the slope, this is negative. At that time you can say your function is decreasing. Here you can observe one thing. So from here to here your function is increasing, and from here at this point your function is constant. That's why this point function is constant. That's why f dash of c equal to 0. That is this tangent is parallel to x axis. Now from here to here your function is decreasing. So your function is decreasing. So from here to here function is increasing. F dash is positive. From here to here function is decreasing. F dash is negative. And at this point slope is 0. That is here. Here tangent. So that is tangent parallel to, let's say, x axis. So here tangent is horizontal, that is horizontal tangent which is parallel to so x axis. So here this is my f dash of x. Now here this is slope, this is greater than 0, increasing, less than 0, decreasing. So here slope parallel to x axis. Now find here. Now find, I want to find. So here y d2y by dx square, which is equal to f dash of x. So here this is the curvature of the curve, or we can say slope of the slope. So here this is the double derivative. So this indicates the change in slope. So here this is the main point. So which help to find the whether your function has maxima or minima. So from here f dash of c equal to 0, you can solve this equation. You will get here you will get point here. I will explain this. So here f dash of x equal to 0. So here the point at which here f dash of, let's say, c equal to 0, that c point is called critical point or stationary point. That c point is called stationary. So here that is stationary point. Here stationary point. Here now I want to define, now I want to find the double derivative, that is d2. So here d2y by dx square, which is equal to f double dash at x. Now so this is double derivative of my function represent the curvature of the function. So here I will define curvature of curve, or we can say slope of the change of the slope in x direction. Here in single direction, here change of the slope, we can say the change of the slope. Now here let's say f double dash at, so this critical point here, f double dash at c is greater than 0, or f double dash at c is less than 0. If f double dash at c is greater than 0, at that time your function has minima, and f double dash at c, so minima with minimum value here, with minimum value at this point. And if f double dash of c is less than 0, then your function has maxima with maximum value at that critical point c. So this is the, and if f double dash at c equal to 0, then we can say no conclusion about the function. So or we can say test fail. So here this is test fail. So here this is the maxima and minima of your function in single variable. Now I want to define maxima and minima of your function in two variable. Now here in single variable, so z equal to y equal to f of x. Now here I want to define function in two variables, so that becomes the surface. So in three-dimensional space, let's say z equal to, so here f of x comma y is a, let's say, is the surface in three-dimensional space, which is the surface here, surface in three-dimensional, this is space. Now here I want to find the maxima and minima of a function in two variables. Let's say f of x comma y, where x and y is the variable which are independent variable, and z is my dependent variable which depends on x and y with respect to the function f. Now first find the partial derivative of z. So here partial derivative of z with respect to x, so that is dou z by dou x. So this gives the slope of my surface along the x axis. So here fx equal to dou z by dou x, which is equal to, which gives the slope of, here slope of surface along x direction. So which gives the slope of my surface along the x direction, and find fy equal to 0, fy equal to, so dou z by dou y, which gives slope of my surface along y direction. Here this is the slope of my surface along the x direction. So here, and this is the slope of my surface along the y direction. Now here now we have to solve fx equal to 0 and fy equal to 0. So combinedly, when fx equal to 0, so this fx equal to 0 slope of the curve along the x axis, and fy equal to 0 slope of the curve along the y axis. When fx equal to 0 means my surface is flat along the x direction. So here fx equal to 0, this represent here my surface flat along x direction, and fy equal to 0 represent surface flat along y direction. Here fy equal to 0 surface flat along the y direction, and fx equal to 0 surface flat along the x direction. When fx equal to 0 and fy equal to 0 at some point, so here this indicates my surface flat along the x direction as well as y direction. This combinedly gives here my surface x here flat along x and y direction mutually. So means here x, so this means that fx equal to 0 and combined fy equal to 0 means my surface is along flat along the x and y direction, flat along the x direction as well as y direction. This is indicates, so here the point at which, so in the same way here f dash of x equal to 0, that is my critical point. The point at which fx equal to 0, fy equal to 0, that is my stationary point, or we can say critical point, pair of critical point. Here the point at which the point, let's say at which fx equal to 0 and fy equal to 0 is called we can say stationary point. Now I want to find the nature of my function z equal to f of x comma y at this point. Now, so here this is my partial derivative along the x direction keeping y as constant. This is my partial derivative along y direction keeping x constant. Now I want to find, let's say here r equal to dou 2f by dou x square. So here this represent bending of my surface along the x direction, or we can say bending of my surface along the x direction, or we can say curvature of my surface along the x direction. So this gives curvature. So here we can say bending of surface along x direction, and in the same way here I am defining t equal to dou 2f by dou y square. This represent bending of my surface, a curvature of my surface along the y direction. So here I am writing bending of surface along, this is y direction. Now here your function is in two variables. So this represent the bending of my surface or curvature of my surface only in x direction, and this represent bending or curvature of my surface only in y direction. What about both x and y direction? So here this is the quantity where s equal to, so dou 2f by dou x and dou y, which represent the twisting of my surface along x and y direction combined, so along x and y direction. So here I will write this as twisting of my surface, twisting of surface in x and let's say y direction. Here this is bending in one direction, this is bending in y direction, this is the twisting, here this is the twisting of my surface in x and y direction. Now here, so from here we will get fx equal to 0, fy equal to 0. This is flat along x direction, flat along y direction. The point at which fx equal to 0 and fy equal to 0. So here that means flat along x and y direction. That point is called stationary point. Now I want to find, so this is my RST. Now I want to define the nature of my function at this point. So here nature of my, so here I want to define RST at this point. Now here define, so now define d equal to here RT minus s square. So here this is the determinant comes from the Hessian matrix. So dt equal to d equal to RT minus s square here, which is greater than 0. Now just observe one thing. So this is the bending of my surface along x direction. This is the bending of my surface along the y direction, and the product of this r and t gives the total bending of my surface along both x and y direction. So here if this is x bending of my, so let's say this is the surface, so if bending along the x direction, and let's say this is the bending along y direction, this r and t, the product of this dou 2f by dou x square, dou 2f by dou y square gives the bending of my surface along both x and y direction. So this is my, so here this quantity, so here RT denotes total bending. So here total bending of surface along both direction, along x and y, this is direction. Now this is total bending of my surface along both the direction, yes, x and y, and this is the total. Here S square denotes total. So here total twisting. So total twisting of surface along x and y direction. Here along x and y direction. Now just observe one thing, the difference between, so here d equal to, so here bending, here bending of surface minus, so here twisting of my surface. This is the here difference between two. So this difference indicates, so here if bending is more than twisting, at that time this so here if bending is more than twisting, at that time this difference is strictly greater than 0. This says that your surface is bending either in upward direction, bending in downward direction, or bending in downward direction simultaneously, both from x and y direction. That is, here if bending is greater than twisting, at that time either your surface downwards or your surface forward. So here upward. So either your surface bend upward, so means make the bowl, either, or your surface bend downward, which open at lower side, so which indicates dome. So here if bending is greater than twisting, so if bending is strictly greater than twisting, at that time this difference is strictly greater than 0. At that time this indicates either your surface bend upward or bend downward. So here this is the case when bending is strictly greater than twisting. When bending is greater than twisting, this overall difference of these two functions, so overall difference of this two quantity is strictly greater than 0. So now another case is that, so here this is my one case. The second case is that here if bending is less than twisting, so here that is twisting is greater than bending. So what happens at this time, when your twisting is greater than bending, at that time this difference of these two quantity is less than 0. So here is less than 0 at that time. So here this indicates that, so here your surface move in one direction, move upward, and in another direction move. So here bend in your one direction, your function bend upward, and in another direction your function surface downward. So here in one direction upward and another direction downward, that is called the saddle point. So this is my saddle point case. Now here, and one more case. So here if bending is equal to, so here if bending is equal to twisting, so at that time d completely 0. So here test fail, we need to move for again higher derivative. So here this is the case. So now I will explain. So here this is the bending and twisting. Now when your function has maxima and minima, I will explain. So here this is now, so this is my rt minus s square is greater than 0. This indicates the simultaneous, means this indicates my surface either move, so my surface bend either in downward direction or in upward direction. This indicates rt minus s square. Now if rt minus s square is greater than 0, so here I will write the case when your function has maxima and minima. Here if rt minus s square is greater than 0 and r is greater than 0, here if rt minus s square is greater than 0 means either bend in downward direction or forward direction, either downward or either forward, and r is greater than 0 or t is greater than 0, anyone. So here r is greater than 0 or t is greater than 0. So here I will write only r is greater than 0. At that time your function has minima. So here your function has minima with minimum value. So here with minimum value at that the pair of critical point. So here from this. So let's say with minimum value f of a comma b. Let's say a comma b is the critical point. Let's say a comma b is the stationary point or stationary point. stationary point. Now, if rt minus s square is greater than 0 and r is greater than 0, at that time your function has minima with minimum value f of a comma b. And second case, here if rt minus s square is greater than 0 and r is less than 0, then your function has maxima with maximum value. So with maximum value at a comma b, this. And third case, here if rt minus s square is less than 0, at that time you can say your function neither has minimum, function here neither has minima nor maxima. So that is the saddle point case. And fourth case, so here if rt minus s square equal to 0, no conclusion, or we can say no conclusion, or we can say test fail. So here, so this is the working rule. How to find the working rule of the maxima and minima? First solve the partial derivative of f with respect to x and equate to 0. So with the help of that, and after that partial derivative of f with respect to y and equate to 0, you will get the system of equation. So here with that, just solve this two equation. You will get the value of x comma y. So here you will get the pair of x comma y such that which satisfy this both the equation. So that pair is called the stationary point, and we have to find the nature of your function at that stationary point. If at a comma b, so if at a comma b rt minus s square is greater than 0 and r is greater than 0, then function has minima with minimum value this. If at a comma b rt minus s square is greater than 0 and r is less than 0, at that time your function has maxima with maximum value this. And if at a comma b rt minus s square is less than 0, then function neither has maxima nor has minima. So we can say that is the saddle point. So in that case, that stationary point becomes the saddle point. And if rt minus s square equal to 0, then test fail. There is no conclusion. So now I want to solve this one example so that you will get one idea. Now, so here function is given f of x comma y equal to x square plus y square plus 6x plus 12. So discuss the maxima and minima of your function. So here, so function in two variable. So here given function, given f of x comma y equal to x square plus y square plus 6x plus 12. So first step we have to solve the partial derivative of f with respect to x and f with respect to y. So here first step, solve dou f by dou x equal to 0 and dou f by dou y equal to 0. So here I want to solve these two equations. With the help of that, I got the pair of a comma b, that is my stationary point or critical point. So here dou f by dou x equal to 0, dou f by dou x which is equal to 2x plus this is 6 which is equal to 0, and dou f by dou y which is equal to here 2y equal to 0. Let's say this is my equation 2, let's say this is my equation 1 and this is my equation 3. Therefore this implies y equal to 0. Therefore equation 2 becomes, so here put y equal to 0, and so from 3 y equal to 0, and from 1, so here from 2x equal to minus 6, therefore x equal to minus 3. Therefore the pair x comma y which is equal to minus 3 comma 0 here, which satisfies this both the equation. Therefore this is my stationary point. Therefore minus 3 comma 0 is a stationary point. Is my stationary point. Now I want to find here. This is my dou f by dou x. Now I want to find r. So r equal to dou 2f by dou x square. So here r equal to dou 2f by dou x square. This is simply 2, and s equal to dou 2f by dou x dou y. So here partial derivative of this function with respect to y. So this is 0 and t equals here dou 2f by dou y square, which is equal to, so here this is 2. Now here now at here minus 3 comma 0. So at minus 3 comma 0 r equal to, so here r equal to, so that is dou 2f by dou x square at this minus 3 comma 0, which is equal to simple 2. So here there is no variable, that's why here I am writing so 0 and no need to write this. So here directly write which is equal to, so which is equal to here 2 and s equal to directly 0 and t equal to, so here I will directly write 2. Therefore rt minus s square equal to, the value of r is 2, value of t is 2 minus 0 square, which is equal to 4 minus 0, no need to write, which is strictly greater than 0. So here rt minus s square is greater than 0, and here you can check r equal to 2 is strictly greater than 0. When rt minus s square is greater than 0 and r is greater than 0, at that time your function has minima. Therefore function f of x comma y has minima at critical point 3 comma 0. Therefore f at here minus 3 comma 0, which is equal to, so just put x equal to minus 3 and y equal to 0. So here minus 3 square plus 0 square plus 6 into minus 3 plus 12, which is equal to 9. So this is 0, this is minus 18 plus 12, which is equal to minus 9. So which is minus 9 plus 12, which is equal to you can say 3. So here this is minus 9 plus 12, this is 3. So therefore f of minimum at 3 comma 0, which is equal to 3. This is the minimum value of my function at critical point minus 3 comma 0. In this way we can solve. So here first of all we have to solve dou 2f by dou f by dou x equal to 0 and dou f by dou y equal to 0. So here with this system of equation you will get the pair of x comma y. That pair of x comma y is your stationary point, and after that find r equal to dou 2f by dou x square, s equal to dou 2f by dou x dou y, and t equal to dou 2f by dou s square. So here after that now at this point we have to find the value of r, s and t. So here I am directly writing because so r equal to just constant, no variable, s equal to constant, t equal to constant, that's why no need to find. So here if variable is not there, so there is a meaningless to find the constant. So here at each and every point the value is same. So here at minus 3 comma 0 is same, or at 100 comma 0 is same. So that is constant function. So here rt minus s square is greater than 0 and r is greater than 0. When r is greater than 0 and rt minus s square is greater than 0, function has minima with minimum value this. So here the minimum value of my function at minus 3 comma 0 is 3. Thank you.